Okay, so going back to continuity for just a second, they had three conditions for us. F of C had to be defined, the limit as you approach C has to exist, and then those two things had to equal each other for condition number 3. Now, digging into continuity just a little bit further, we're going to start to classify our different types of discontinuities. So here's basically a definition for us. A discontinuity is removable. A discontinuity is removable if a limit exists at that x value. A discontinuity is removable if a limit exists at that x value. So earlier in section 1.4, I think it was just part 1, all we had to do was say not continuous at x equals 1 or whatever it was. We just had to say it was not continuous there. Well, now not only do we have to find those x values, we have to classify them as removable or non-removable. So I'm going to put a picture of a graph up here. You might want to just kind of sketch this down so you have a good idea of what this is going to look like. This is just an example of a function that has a removable discontinuity. It's removable if the limit still exists at that x value. Now this is just kind of a general graph here. I'm not even really putting any numbers up here, but I would say right here at that hole, it's not continuous at that hole because it would fail condition number 1. F of C is not defined here. But taking it one step further, I could go on to say that the discontinuity is removable. Okay? It's not continuous because condition 1 would fail, but it's what we call a removable discontinuity because you could still find the limit. The limit would still exist, but it's not continuous. Okay, now we also have non-removable discontinuities, which is basically just the opposite, but I'll show you a couple pictures of what that could look like. A discontinuity is non-removable, bless you, if a limit does not exist at that x value. A discontinuity is non-removable if a limit does not exist at that x value. It's just the opposite of removable. Okay, sometimes I like to think of removable, the word removable, as fixable. This kind of discontinuity is easily fixable. If I just filled in that hole and made it a point, then it would be continuous. So removable discontinuities are more fixable. Non-removable, there's a little bit more of an issue. This would be an example of a graph that has a non-removable discontinuity at x equals c. If you run through your conditions for continuity, condition 1 is fine. F of C is defined because there is a point up there. But the limit as you approach C did not exist. This is basically just when condition 2 fails. So a discontinuity is non-removable if you're not able to find the limit. So it could be something like this, where they're just approaching two different y values, or I kind of had to draw this one in by hand, but it could also be something where there's an asymptote at that x value. So coming in from the left, you're going all the way up. coming in from the right, you're going all the way down. That would be another example of a non-removable discontinuity at x equals c. C can be anything, but we're just kind of showing you in general what could happen. Removable limit still exists, but non-removable, the limit does not exist. Kind of going with condition 1 and condition 2 of continuity. All right. Now, I will say that we are going to use our graphing calculators quite a bit today to look at the graphs, but we have to be careful because our graphing calculators do not show us holes. Like if there's a hole at x equals 4, then your graphing calculator is not going to put an open circle there. You have to figure out other ways to find the hole. So again, our calculator is going to be helpful, but there are some other things that we'll have to look at without our calculators. Okay, so this is pretty much the directions all day today. And it says, find the x values, if any, find the x values, if any, at which f is not continuous. Find the x values, if any, at which f is not continuous. And then it says which of the discontinuities are removable or non-removable. Which of the discontinuities are removable and non-removable? So which ones have limits still? That would be removable. Which ones do not have a limit? That's what we're looking for. Now, I'm going to try and kind of give you some hints along the way of things that you want to look for. So here is example 1, and it says f of x equals x cubed minus 2x squared plus 1. X cubed minus 2x squared plus 1. Now I'm going to write something down up here that we can actually apply to every single problem today. I'm going to just write, think about your domain killers. Harsh term there. Domain killers. That is going to help us find any x values that we should be suspicious about. Thinking about your domain killers, that helps you find the x values that you should be worried about. Now, domain killers, one of them was the square root of a negative. I don't see any square roots here, so I'm not worried about that. The other domain killer was dividing by 0. And I really don't see any fractions here to make me worry about that domain killer either. So I'm not getting any clues from the function. So it may not hurt to go ahead and just graph this to make sure that there's nothing funny going on with the graph. I'm not getting any good ideas of any x values that I should be worried about. So this is just kind of double checking things a little bit. X cubed, and it was minus 2x squared, and then plus 1. If you see any asymptotes, then you should be concerned. Or if you see any breaks in your graph where there's something up here, something down there, you should be concerned. But this, I mean, it's just a continuous curve here. I don't think there's going to be any x values where it's not continuous. So all I would say on this problem is I would just put continuous everywhere. I don't have any x values where there are discontinuities. So you don't even have to go on to classify them as removable or non-removable because you don't have any. So that's all we'd have to say on number 1. Okay, now I'm going to try a few more here. Example 2, we spent a lot of time in trig graphing these trig functions. Those are fond memories. But if you don't remember what sine looks like, then you once again can go ahead and graph it. I'm not seeing either of my domain killers here, but that doesn't always apply to trig functions. So I'm going to take 2 seconds and graph this to see what I'm working with. Sine of 2x. There it is, the good old sine curve. Now, if it was tangent or cotangent or secant or cosecant, those all had asymptotes that you would have to worry about. But sine curves and cosine curves, remember cosine just starts up instead of down, those curves are going to be continuous everywhere. Unless there's some kind of a fraction with the trig function in it, I don't think we'll have to worry about that. So I would say, again, for this one, that it is continuous everywhere. Nothing to worry about with sine curves or cosine curves. Remember, that could change, though, if it was a different trig function. Okay, well, not a whole lot going on yet, so let's keep moving. Example 3, f of x equals 4 over x minus 1. 4 over x minus 1. Now, once again, I wasn't really able to do them earlier, but you do want to think about your domain killers, okay? Because remember, your graphing calculator might not show you everything. So thinking about our domain killers, the x value that I'm concerned about here is x equals 1, because I know if x was 1, 1 minus 1 is 0, and I would be dividing by 0. That's the x value that I'm concerned about. So more than likely, that is going to be one of our points of discontinuity. Now, we still have to classify it as removable or non-removable. So for that part, you might want to look at the graph because it all depends on if the limit exists. So once again, I'm going to type this in because I need to figure out what this looks like. Now, please be careful. When you type in 4 divided by x minus 1, you want your calculator to divide by the entire x minus 1. You have to put that in parentheses, otherwise it just divides by x and then subtracts 1. That's not what you want. So remember, we were concerned about x equals 1. So I can actually see this pretty clearly on my graph. At x equals 1, there's a vertical asymptote. So as far as removable or non-removable, I just need to figure out if the limit exists as I approach x equals 1. But we can tell, coming in from the left, you're going all the way down. Coming in from the right, you're going all the way up. I would say the limit does not exist. So x equals 1 is going to be non-removable. That was the definition of a non-removable discontinuity. It's if the limit does not exist at that x value. So it helps to see it on the graph, whether or not it's removable or non-removable. Okie doke. I'm going to try some more here. Example 4. f of x equals x minus 4 all over x squared minus 16. The first thing you should do is figure out what x values you're concerned about. Okay, now right here it was pretty easy to figure out it was just 1. If you want to be technical, to figure out these x values, you're basically setting the bottom equal to 0 and then solving for x. So add 16 to both sides, square root both sides. I'm worried about positive 4 and negative 4. I like to do this part first because then when I graph it, I know where to look. I need to look at positive 4 and negative 4. Now I would probably use parentheses around the top and the bottom when I went to put this into my calculator. Here we go. The whole x minus 4 divided by the whole x squared minus 16. Gonna have to erase my asymptote from earlier. Okay, we're looking at positive 4 and negative 4. I need to classify what these discontinuities are. Are they removable or are they non-removable? Now, I'm going to start with the one that's more obvious. Negative 4 is a vertical asymptote, so the limit does not exist as x approaches negative 4. I would say that that is non-removable. The limit does not exist as you approach negative 4. Now, here's where I said our calculator doesn't really help us a lot with wholes. If we hadn't got x equals 4 earlier from the function, we may not have known that there's actually a whole where x equals 4. Our calculator doesn't show it, but if you trace to where x is 4, it's not going to give you back a y value because there's a hole there. Now, if you think about a hole right here at 4, you can still approach 4. It's not that the limit does not exist like what happened over here. Even if there's a hole at x equals 4, I can still come in closer and closer from both sides and I could find the y value that I'm approaching. So I would classify this as removable because you can still find the limit, it's just that there's a hole there instead of a point. Okie doke. Any questions about that one? This is why I suggest finding those x values first. If you just graph that, you may not have picked up the positive 4 one. It doesn't show it on your calculator. Okay, I think I've just got a few more. Number 7 is the last one today. So, example 5, f of x equals absolute value of x minus 4 all over x minus 4. Which x value should we be worried about? 4. I need to look on my calculator at where x equals 4, and then I should be able to figure out if it's removable or non. So here we go. Thank goodness for graphing calculators. Absolute value, go to math, write 1, and it should be option 1. We want absolute value of x minus 4. If your calculator sets up parentheses for absolute value, if you've got like an 83, something like that, make sure you end the parentheses and then divided by parentheses x minus 4. Anytime you type in a fraction, gotta make sure and use some parentheses. So I'm concerned about 4. We knew that from earlier. Would you call this a removable or non-removable discontinuity? Non, yeah. As you get closer and closer to 4, this limit would be -1. That would be +1. The limit does not exist, so we've got another non-removable discontinuity. All right. Now, last couple here. Still kind of the same thing. Number 6 says f of x equals x plus 3 all over x squared minus 3x minus 18. First thing you need to do before you graph this is you need to figure out what x values you should be concerned about. Now think about setting this equal to 0 and solving for x. You're going to have to factor this to solve it for x, or I guess you could use the quadratic formula if you really liked that. But factoring is usually easier. Signs will be different because the sign on the right is a minus. So two numbers that multiply to -18 and add to -3. Yes, -6, +3. So by the time you break those apart and solve them for x, I get back x equals -3 and x equals +6. Those are the values that you need to look at on your graph. You need to look at where x is -3 and where x is 6. So here we go. Couple more times. I've got x plus 3 in parentheses divided by x squared minus 3x minus 18. Make sure I did that right. Okay, so I already forgot. Where was it? -3 and +6. +6 is the easy one. If you go to where x is 6, the limit is not going to exist there. So I would call this non-removable. Now what about -3? What's that one going to be? It's just removable. You could still find the limit as you approach -3. It's just there's a hole there instead of a point. So again, one of each type. X equals 6. That was the asymptote, so that was non-removable. And that was just a hole, so that would be removable. All right. Now, last one. It's always good to kind of think about piecewise functions when you're talking about continuity and limits. So here we go. Example 7, f of x equals x squared minus 1 when x is less than 1, and then it equals just x when x is greater than or equal to 1. When you have a piecewise function, normally the x value that you're concerned about is this one. These numbers are always going to be the same right here. So I am going to graph this, but I'm thinking I probably need to look at where x is 1, because that typically, with a piecewise function, is the one that you should be concerned about. Now hopefully you remember how to do this, because this is something you should know how to do. X squared minus 1, that is when x is less than 1, in parentheses, and stick another plus sign with more parentheses. Second behavior is just x, and that is when x is greater than or equal to 1. I'm going to make sure I did that right. Okay, I'm looking, not here anymore. And if you see right here at where x is 1, the limit from the right would be 1, and the limit from the left would be 0. The limit does not exist at x equals 1. So for this one, I would have to say x equals 1 is non-removable. You cannot find the limit as you approach 1. Okie doke. Any questions about those? Remember, graphing calculators don't show you holes, so make sure you find your x values ahead of time. This is C23 from pages 96 to 97. We're going to do 37 to 54. And you've got about 15 minutes left, so see if you can't get some of this done. I may have some quizzes to pass back here in just a little bit too.